inbuilt. Are you familiar that in the past calcium chloride was used as an inhibitor, as an accelerator? It's not an issue on its own, but it becomes an issue if you have water. If water comes in, then the equation will change. And you have freeze thaw and all of the other shrinkage and all the material related property. So, and this is for UK as a whole. Northern Ireland is a bit more straightforward. We're the largest concrete producers in the UK. We make more concrete. We make 80% of the concrete. Have you seen Northern Ireland as a map? So this is my map skills are. So this is UK and that's Scotland and this is Wales. So Ireland is about that size. And Northern Ireland is about that much. It's very small. Actually, much smaller than Scotland even. For that island nation, we produce 80% of UK's concrete. We make it, we ship it across the UK, and it's still cheaper for us to deliver to London than somebody who lives 100 kilometers from London to deliver. That's a different economics, okay? Part of the reason we make good concrete is we have very good quality aggregates. Most of the cement producers in Europe are based in Ireland. Most of the European cements are owned by Irish Cement Association. They control the market, which means we can produce a lot of cement. So for Northern Ireland, the issue is different. Quality of aggregate and quality of construction means majority of our structures, 80% of our structures, chlorides are the only issue. Chlorides are really a big issue for us. Okay? So this course will look at chlorides and carbonation because I presume that's very common here. Is carbonation a big issue here? Okay. It'll be a very big issue closer to the industrial zones or more industrialized cities. I'm sure it's an issue in Bangalore anyway. So yeah. So let's then focus more on carbonation and chlorides, because if you look at climate change, I think one of the primary things that will change is the CO2 concentration. And it has a direct effect on the structures. Some of it is good, some of it is not good, so we'll look at that. So that gives you a breakdown of where we focus our effort. And I have some slides on the concrete. Given that most of you are quite familiar with concrete, I don't really need to spend much time, so I don't intend to. Anybody can make concrete, am I right? Anybody can make concrete. All you need is a mixer, okay? And that's part of the problem, that everybody can make concrete. Cement is so hydraulic that you just add water to it and just throw some stones. Concrete. It's not really difficult. It shouldn't be. It's an easy material. For a general purpose, concrete should be the case, but not for structural concrete, not for concrete that's designed to last. So through this slide, what I'm trying to say is the effective water binder ratio. So if you have the same amount of cement particle in an area and you increase the water, i.e. you have a higher water binder ratio concrete, it disperses itself. That's the only way you can manage. These are charged particles. Cement is charged particles, which means they'll tend to disperse, which means the network will be very loose. So anything that's looking to come from outside, it's much easier for it to come from outside. Most of the things that are coming from outside, whether it's water, chlorides, carbon dioxide, sulfate, or whatever, they are charged particles. So as further the charged particles are, it's easier for them to come in. Closer the charged particles are, harder for them to come in. It's not just the gap, it's how much force these things can exert to whether that's chlorides or carbon dioxide. So it's a very simple equation. And this is what a typical cement structure would look like. That kind of structure refers to your calcium hydroxide plates. It's a very soft plate that you can see when you're working in the nanostructure area. And the calcium silicate hydrate looks like a needle, porcupine. And that's your calcium aluminate, calcium ferroaluminate, or calcium sulfoaluminate. So that's your structure. That's what gives you the structure of cement. So assuming something is to come in from outside, this is the mess in which it'll have to go through. Okay? So if you have a higher water binder ratio, which means it can find its way down, it'll take time, clearly it's a charged particle. And that's the difference between cement and the clay particle. Clays are charged as well, but the pore structure might be, you can have comparative pore structure by making concrete weak. The rate of transport will be decided by the amount of charged particles you have and the way you put them together. This is why when you look at, I think even in the Indian standards, it's very strict on, am I right in saying the Indian standards are strict on water content or water binder ratio? For structural concrete, does it say the water binder ratio shall be less than certain? Okay. That's the reason why they're saying it. So we're going to be battling with some of these guys later on. Calcium silicate hydrate, your structural part of your cement. Calcium aluminate hydrate, which is the part that you love if you're working in the industry. That's faster reacting stuff. It's great from a durability perspective. I'll explain as we go along. This is good for durability as well. But a lot of that means it's not really good. So there has to be a balance between them. And this is what I was saying, that this kind of technology is well known for cement industry. They can make it, they can reverse engineer it, they can make it whichever way they want it to have a desired property. And this is a critical member, quite often overlooked, but that's your defense system for chlorides as well as for carbonation. Okay? Happy enough? Okay. You can use a microscope. Majority of you are researchers, and you know that you can look at concrete in different layers. If you look at millimeter layers, you can physically see it. Nanometer or micrometer, you probably need an optical microscope or below. And then nanometer, you need much more sophisticated tools. But you can. In the same way as you can look at it, you can also build them back. So if you look at NIST or TU Delft, they have microstructure models which you can put everything back. But not generated from that, it's more theoretical. And they're too far away from millimeters. Okay? So the strength of concrete is provided by aggregates. Am I right? If I have a pack of aggregate and I'm confining them from expanding, can I get similar strength as concrete? So my question is very deliberate and very much controversial. So I'm taking a box which is steel cladded. Okay, it's solid steel here. Solid steel here. I have a pack of aggregates here. And I have another pack here which is concrete. There's only aggregate in here, okay? It's well compacted. So my question is, can I get comparable strength as concrete with that? Anybody from geotechnics background? Okay. Well, you're all geotechnical person anyway, you would have learned it. So there's no lateral expansion allowed. It's confined. Can I get it then? Sorry? Yeah. So it's confined. I'm confining it. Can I get the strength? How many of you think I can get closer to it but not exactly? Closer? No? Have you tried it? If you confine it, you can get closer to it. I'm not in no way saying you will get anywhere near it, but you get closer to it. Part of the reason is, and depending on the stone clearly, okay? So if you're using good quality basalt or quartz stone, and it can transfer the load effectively, you've compacted it quite well, you're then testing the stone if you confine it. Except the slips of the stones will then determine its failure. And that's what we expect the concrete to do. Concrete, you can't confine the concrete forever, so we're expecting an internal confinement from within concrete. So what is the job of my cement? Is it to confine the aggregates and keep it in place? We know concrete is very good in compression. Yeah? Is concrete good in shear? I did ask any structural engineers. So we design the steel quite often assuming the shear is carried by steel. Whether you use a strut and tie method or any other method, you design the steel for taking the shear, which means we're sparing the concrete from taking the shear strength. So the only job of concrete therefore is just to provide the compression stress on the top of the beam if it's in flexure, and to keep the aggregate in place structurally. Okay, but durability wise, it has another function. It is trying to keep the steel protected and trying to keep the steel in place. Okay, those two things are important, because if you look at the top and bottom steel of a reinforced beam, you do need them to be at a set distance. Ideally, you prefer them to be further away. You get the largest lever arm, you get the best bending moment. But that comes with the consequence, either the beam is too big or the cover is too low. But you want them to be in a set position. So concrete's first job is to keep them there. Second job is to protect them from outside elements. Now that could be fire. Concrete is good in fire protection. Or it could be salt or water, anything else. And the third protection it's providing is to keep the aggregates in place. Once the aggregates are perfectly in place, there will be shear interlock between the aggregates, which means even your steel may not have to take the shear. The concrete will be able to take the shear because of that aggregate interlock. So these are the functions of your cement. It's meant to do all of this. And it has the chemical nature to do all that it needs to do. But what we need to do is redesign it so that it can do these jobs and more. Okay. The typical issues that you can expect in concrete are around the aggregates. Okay. Around the aggregates is very critical, for the same reason that I'm saying. This is why I started with that, because if I had the aggregates interlocking and then you pour the cement slurry into it, you can make really good concrete. There's a lot of people working on that kind of theory, minimum cement theories and all. But concrete is essentially not that way. We make the concrete flow these days, like self-compacting or self-flowing concrete. It's a requirement for certain structures. It's because the steel might be too complex otherwise. And in the UK, the precast production, now 80% of the precast is self-compacting. Because you don't need vibration, great. The UK requirement for concrete is that it has to shine. The surface has to shine. So self-compacting is the only way. They make a metal mold, they reverse the mold, they pump the concrete in, and they might have vibration systems on the top, or the whole bed can vibrate. But when you lift the mold away, the surface concrete will have it'll look like glass, essentially. And quite often the architects might say it needs to shine and it needs to have that color. They might give a piece of paper and say it needs to have that color. For those who are working in concrete will know this is incredible, because the aggregates play a part in the color, so which means you have to change the aggregates. I've learned cases where they bring the aggregates from China to do the concreting. Imagine the distance, but they have to do it to get that exact color. Clearly they make money, otherwise they wouldn't do it. But it is an incredible art. So coming back to it, in terms of durability, this is a very important zone for us, because that interlock that it provides, connectivity between these aggregates and keeping them in place, is our structural capacity. And in terms of durability, that is a fully formed aggregate now put in place into a new material. So that interface needs to be solid. If it is not, then it's just a conduit for things to go and things to flow. Looking down in a backscattered electron microscope image, that is your aggregate, so it's much more enlarged. So these kind of techniques allow you to go further and further and further down to look at bigger picture. So this is your stone, which is typically 10, 20 mil. And you can see micro cracks around it. And that's due to differential shrinkage between the differential shrinkage. It's due to shrinkage of the cement system, but the aggregates is just remaining in place. So that difference in movement when it's curing can cause micro cracks. Stresses can cause micro cracks. The aggregate itself can be reactive, it can cause micro cracks. And everything else is a pore structure. It's quite a difficult diagram to figure out when you look at the image initially. And that's where the medical technology is so advanced. I'll show you in a minute. You can color it. The software is so advanced that, you know, in the CT scan system, it's very similar to that. You can give a color to a particular color and highlight it, which means you can say all of these reds are your pore network, whether they're due to microcracks or whether they were already there. Which means if I put water here, it can quite easily move down. Okay? Quite easily is just the exaggerated word. It's not that easy for it to move. Remember, they're all charged particles, so it's not easy for even water to move that fast. But it's in the order of 10 to the power minus 8 to 10 to the power minus 12. So it's quite low, but it's enough, because all these 10 to the power of 8s will go, when you look at 100 years, they will go really fast. Okay? So, that's your aggregate, and this is your interfacial zone. And if the aggregate is expansive in any way or reason, that zone will be filled by reaction products, which are much more weaker. And then coming back to here, there's no interlock anymore. And also they produce a layer of very weak material where things can flow. So this is the story of our concrete. I can ignore that. This is not a cross-section of our structures in Northern Ireland, but it's not too far from it. So all the de-icing salt used in the road above has come through the expansion joint, which is quite nicely placed on the top of a pier. It's very easy to put the expansion joint there, because the deck, just like this, a deck has just been put in place. There's a gap there, and you'll have two solid legs, or a solid leg below it. Much easier to put it there, but it's extremely difficult to maintain that kind of structure, because the water will go in, go through the crack, go through the expansion joint. It has to go somewhere, and it'll just go on either sides of the pier. And this water has a lot of salt in it. Net result, you can see the water there, and you can see the patch. Patch is whatever corroded away, but the rest is corroding its way. In addition to that,